chapter, and we should be done. Don't forget the test will become available today after class.
Oh, it's already available.
And it'll be available after class.
It's already available.
Oh, it's already available? Oh, I must have not been. Anyway, well, y'all know the routine. It's due by Sunday at 11:59. Okay, so like we've been talking, what becomes important is the movement of the materials. And we have talked a lot about these particles that are carried in the blood that are important, these nutrients, the things that the cells need. So we get to see that diffusion is very important because, remember, diffusion, movement of particles, okay? So our glucoses, oxygens, the CO2, hormones, electrolytes, all these things get to do their diffusion across these capillary cells so that we can get them to that extracellular fluid for the cells to use. The one that we talked about, transcytosis, for something to move across the cell. Well, do you guys remember pinocytosis, cell drinking, how the plasma membrane can just wrap around some fluid and whatever's in it gets to be moved into the cell? And receptor-mediated endocytosis, do y'all remember that one from part 1? Okay, the cells may have little receptors on them, and when enough particles actually get into those receptors, it just kind of folds in the membrane and brings in the material. It's really kind of cool. We have transport vesicles that can actually exist in the cell and help move a particle from one side of it to the next. These are just ways that we have the movement. Exocytosis, this is how some cells will get a particle out of itself. So when we look at materials and their movement, for example, fatty acids, one of the things that happens with that could be that little receptor mediated, where once we get enough particles, they can be brought into the cell to be used. Insulin would be a good example of the cell that has made the insulin and putting it out so that it can make it to the bloodstream for it to be used by other cells. So, in these different types of movements, okay, that occur, this is how we're going to actually get materials to cells to use and get material back into the blood to get rid of waste and so forth. One of the things about the movement of materials, which we've talked about this because I just talked about it with all the extracellular fluid, okay? The filtration and the reabsorption, like I was saying, driven by osmosis. All right? Basically, those pressures. And do you all happen to remember what it meant to be a colloid? Do what, Gabrielle?
Like suspended in the fluid.
This is where a particle gets to keep its properties in the fluid. So if you think back to what I was talking about earlier with extracellular fluid, these are particles. And that means all of this. Do you remember how, for example, we said blood was a colloid? Because blood coming in gets to keep a glucose particle. It gets to keep a salt particle. Okay? The red blood cells carry. Do you remember that? Okay? And based upon pressures, this pressure created by these particles, and then the water moving, that's a colloid pressure. All right, we've talked about this, so that's why I'm not going back over it again. And then what happens based upon these pressures that get created right here, this is how we're going to end up pushing material out or bringing materials in. Got a picture because we've talked about it there. So on my arterial end, I'm going to have my little bit of blood pressure. Remember that? And out here, see how they're trying to represent cells in all of this tissue, and around them is extracellular fluid, is a pressure. And if there is a pressure difference, this will cause material to move. Is everybody with me? Based on what we've talked about for the extracellular fluid. And then on my venous end, where there's little to no pressure, okay? And once again, if there's a pressure out here, I get to move my waist. And there's a pressure from here to here, just in the vessels themselves, not including pressure around them. Going from high pressures to low pressures. All right? So in between pressures in the vessel themselves and then pressure outside the vessels sets up the situation for materials to either move out or materials to move in. Which is kind of cool if you think about it. Now, when we look at variations that can happen with these capillaries, something that I kept mentioning, edema. And the reason for that, this is very clinically significant, okay? This is where we get fluid staying behind in the tissues. This can set up some life-threatening situations depending upon what tissue is getting affected. This is where fluid will enter into this extracellular fluid faster than it makes it back to the venous return. We can have it due to an increase in the filtration. So if you think to those pressures and the movement of materials on that arterial end, if there's an increase in that capillary fluid going into my ECF, such as kidney failure. People who have kidney failure, one of the things that happens, edema begins to build up. Now, as the kidney failure, as the disease progresses, this becomes more apparent, very difficult for them to get rid of the fluid off of their body. It begins to put pressure on lungs, heart, other vessels of the body, okay? And then, dialysis usually has to be, all these things will begin to happen in kidney failure. Right ventricular failure, congestive heart failure, the COPDs, anything that will have an effect on the right side of the heart, because this is where the blood is supposed to return for us to begin the filtration to get rid of it. To, for example, make urine by the kidneys, okay? And it will cause the fluid that should be making it into the through the heart to the filtering and all the other things that should take place. It's going to cause fluid to build up around the body and around the heart, around the lungs, and so forth. We can have it be reduced capillary reabsorption, meaning going back into the venous end to start the return, to start filtration, to get rid of it. So it can be at the arterial end or the venous end. Usually, people, for example, with cirrhosis, one of the things you see happen is they end up getting this real distended abdomen, and the abdomen is very hard, okay? And it's from the fluid buildup in the abdominal cavity. And then, if there's anything obstructing the lymph vessels, the lymphatics, okay, which we will get into when we move into that chapter. A good example, women who have breast cancer, one of the things that can happen if they have a mastectomy, if they're, usually they take out some of the lymph nodes to check and see if the cancer has spread to the lymph nodes, and in some cases they may have to remove a significant amount of those lymph nodes, and usually the women end up with swelling in their arm on whatever side the mastectomy might have taken place, and it's because they can't move the fluid, the lymph, that even though it's a very little amount of fluid, but it does build up if it can't move, and at night they usually have to put on the compression sleeves so that they can push it back up and into circulation for the body to get rid of it. So those are three usual reasons that you'll see edema building up. One of the things that we've got to end this chapter with, the veins. Once we have the blood flow, once we get it to that capillary side, once we get exchanged, we have to remember we've got to return it. Okay, we've got to pick stuff up. We've got to have the venous return. Whew, back to the heart, another typo. There are 5 mechanisms involved with venous return. We get a pressure gradient, not great, just a little bit from the heart. Gravity definitely works against venous return. We are heavily dependent on skeletal muscle pumps. That's what they call it. So as we think about the veins and the return of blood back to the heart, the more movement you have, the more skeletal muscle you're using, more pressure against the veins to push the blood back up towards the heart. The more sedentary you are, the less blood is flowing to the heart. We have a thoracic pump. Breathing. We can affect it, okay? We can do like the yoga and all that sort of stuff that is, focusing on breathing. For the most part, we're dependent on that autonomic nervous system making us breathe. This is all skeletal muscle. These muscles in between the ribs, our diaphragm, as we breathe, we actually create a pump that helps to circulate the blood in this thoracic region. And then those tendinous cords, do y'all guys remember the chordae tendineae that are attached to those AV valves? They create just a little bit of suction every time they flap. Not a lot, not enough to actually generate blood flow like we would think. Because the veins are capacity, where we have a lot of blood stored in the veins. Well, any time that blood cannot meet the demands of the body, meaning cardiac output, that beating of the heart, okay, if there's not enough blood getting pushed out, it's now insufficient. We are not meeting metabolic metabolic needs.